Hello everyone, welcome back to ZypherSpaceCore. Through this example, we are going to understand one of the most important concepts in linear feedback shift register. We will learn how an LFSR generates the sequence, how the feedback works, and how to calculate the period, and finally how to check whether the output looks random or not. This is very important foundation because the stream ciphers and many cryptographic systems use LFSR internally. So, first question is a 4-bit LFSR is defined by a feedback connection C equal to 1001 and initial seed 0101. We need to find the output sequence, the period t, and check whether the probabilities of 0 and 1 balanced. That is p of 0 equal to p of 1 equal to 0.5. Before solving, let's first understand what an LFSR actually does. An LFSR is basically a chain of flip-flop or memory cell. Here we have 4 stages, S3, S2, S1 and S0. At every clock pulse, a bit shift, a no feedback bit is generated and one output bit is produced. The output is taken from S0, which is the rightmost bit. Now let us understand the feedback mechanism. Here the connection vector is C1001. This means the taps are present at S3 and S0. So the feedback equation becomes S3 XOR S0. Now what does XOR means? XOR gives 0 when both bits are same, 1 when both bits are different. So 0 XOR 0 equal to 0, 1 XOR 1 equal to 0, 0 XOR 1 equal to 1 and 1 XOR 0 equal to 1. This feedback bit is inserted back into the register after shifting. And the initial seed here is 1010. So S3 equal to 0, S2 equal to 1, S1 equal to 0 and S0 equal to 1. Since the output comes from the S0, our first output bit is 1. Now let us simulate the first cycle carefully. The current state 0101, the output bit S0 equal to 1. We can calculate feedbackness, that is S3 XOR S2. Sorry, X3 XOR S0. 0 XOR 1. 1. Now the register perform a left shift. After shifting and inserting feedback 1, the next state becomes 1010. And the next cycle, that is cycle 1. Now the current state is 1010. The output comes from the X0, so the output is 0. Now calculate the feedback again. 1 XOR 0 equal to 1. Shift left and insert 1. The next state becomes 0101. Now here we observe something very important. We already returned back to the original state, that is 0101. This means the sequence has already repeating. So LFSR is cycling between only two states, 0101 and 1010 again and again. So the generated output sequence is 10101010, simply alternating between 1 and 0. Now let us calculate the time period. The time period t means how many bits does the sequence repeat itself. Here the pattern repeat after every 2 bits. So t equal to 2. Now for the LFSR, like 4-bit LFSR, maximum possible time period is 2 raised to 4 minus 1, which is 50. But our actual time period here is only 2. So this is not a maximum length of LFSR. Now let us just check whether the sequence is balanced. We can analyze the first 8 bits. 1010, 10. That is the count number of 1s is 4. Also the count number of 0 is 4. So the P of 1, 4 by 8, which is 0.5. For P of 0 also 0.5. So statistically the sequence is balanced. But here comes a very important lesson in cryptography. Even though sequence is balanced, it is still not secure. Why? Because the period is extremely small. An attacker can predict the next bit almost instantly. The sequence is 101010, completely predictable. So the balance alone does not mean randomness. A cryptographically secure sequence must also have a long period predictability, like unpredictability, and complexity. So we can conclude that here the output generated sequence is 1010 repeating, and the time period is 2 and the probabilities are balanced, but the sequence are not suitable for the cryptography. In next example, we will move deeperly into the prediction and period analysis using recurrent relationship. Question is, the LFSR has 4 memory elements. From the output sequence, we know that there's something that is st plus 3, st plus 2, xt plus 4, xt, etc. equal to something 1, 0, 1, 1s, etc. We have to find st plus 4 and st minus 1. The second, the time period t, and third, the maximum period t max of this generator. Here we have a 4-bit LFSR architecture with the 4 stages S3, S2, S1 and S0. The bit shift from left to right and the output is taken from S0. The XOR feedback combines the selected tapes and generate the next incoming bits. Now let us arrange the given output properly. That is ST equal to 1, ST plus 1 equal to 1, ST plus 2 equal to 0, ST plus 3 equal to 1. We need to calculate ST plus 4 and also ST minus 1. So we are basically predicting one future bit and the one previous bit. Understanding the recurrence relationship. Like in an LFSR, every new bit is generated using a recurrent relationship. For a general n-bit LFSR, ST plus n equal to C0 XT XOR C1 ST plus 1 XOR etc. to XOR Cn minus 1 St plus n minus 1. This equation tells us the next output depends upon the previous output and the tap connection. For this 4-bit LFSR, the recurrent relationship becomes St plus 4 equal to St plus Xt plus 1 XOR St plus 2 XOR St plus 3. This means the next bit is generated by XORing the previous 4 bit. Remembering the XOR rules, that is same gives 0, different gives 1. Now let us substitute the values carefully. That is St equal to 1, St plus 1 equal to 1, St plus 2 equal to 0 and St plus 3 equal to 1. So the St plus 4 equal to 1 XOR 1 XOR 0 XOR 1. So we can solve step by step. That is, first 1 XOR 1 equal to 0. So it becomes 0 XOR 0 XOR 1. Next 0 XOR 0 equal to 0 and finally 0 XOR 1 equal to 1. Therefore, St plus 4 equal to 1. Now let us work backward and find St minus 1. Shifting the recurrent relationship one step backward, so we get St plus 3 equal to St minus 1 XOR St plus 1 XOR St plus 2. Now substitute the values, that is St plus 3 equal to 1, St equal to 1, St plus 1 equal to 1, St plus 2 equal to 0, so that it becomes 1 equal to St minus 1 XOR 1 XOR 1 XOR 0, and simply it becomes 1 XOR 1 equal to 0, so the 1 equal to St minus 1 XOR 0 XOR 0, 0 XOR 0, it's 0, which becomes 1 equal to St minus 1. Therefore, St minus 1 equal to 1. Now let us analyze the period of the LFSR. The time period T means after how many cycles does the sequence repeat itself again. For properly designed LFSR, the state can cycle through many different combinations before repeating. For an n-bit LFSR, the maximum possible time period is T max, that is 2 raised to n minus 1. Since this is a 4-bit LFSR, T max is equal to 2 raised to 4 minus 1, 16 minus 1, which is 15. After analyzing the state repetition, we observe that the sequence repeats after 15 cycles, so the T is 15. Now comparing the value, the observed period T equal to 15 and the maximum possible period T max also 15. Since both are equal, T equal to T max, this means the LFSR achieves the maximum possible sequence length. When an LFSR achieves the maximum possible period and its polynomial, that is its feedback polynomial is called primitive polynomial. Primitive polynomials are extremely important because they can generate a long pseudo-random sequence, better statistical property, and improved unpredictability. The maximum length LFSR are widely used in stream ciphers, spread spectrum systems, scrambling circuit, error testing, and pseudo-random sequence generator. The longer period makes sequence harder to predict and reduce reductions and repetitions. So, finally, we conclude that ST plus 1 ST plus 4 equal to 1, ST minus 1 equal to 1, and observed time period T equal to 15 and T max equal to 15. Therefore, this is a maximum length LFSR generated using a primitive polynomial. The next question is, the output sequence of the 3-register LFSR is 00110, where the rightmost bit is the first in the sequence. Find the seed, the period T, and encrypt the plain text. And the message M is given using this LFSR as the stream cipher keystream generator. Here we have 3-bit LFSR consisting of S2, S1 and S0. The output is taken from S0, which is the rightmost register, and the feedback is generated using XOR between S2 and S1. So the feedback equation becomes S2 XOR X1. We are given the output sequence 00110, and the question says the rightmost bit is the first output. So ordered sequence becomes 00110. Now let us reconstruct the initial state of an LFSR. We work backward from the output sequence. From the state analysis shows that S2 equal to 1, S1 equal to 1 and S0 equal to 0. Therefore, the initial seed becomes 110. Now let us understand how this LFSR generates the output. At every clock cycle, the output is taken from S0. The feedback bit is generated using S2 XOR S1, then the bit shift. In initial state 110, so the S2 equal to 1, S1 equal to 1, S0 equal to 0. Since the output comes from S0, the first output bit is 0. The next cycle, the current state become 110. Output 0. Calculate the feedback, that is S2 XOR S1, 1 XOR 1, 0. After shifting and inserting the feedback 0, the next state becomes 111. It goes to cycle 2 and the current states become 111. Output 1, feedback 1 XOR 1, 0. Shift and insert 0 and the state becomes 011. So the current state of cycle 3 is 011 and the output is 1. Feedback 0 XOR 1 equal to 1. Shift and insert and the state become 101. And the current state of cycle 4 is 101. Output 1. Feedback 1 XOR 0 equal to 1. Shift and insert 1. The state becomes 010, which is the current state of cycle 5. 010. Output is 0. Feedback 1 XOR 1, 0 XOR 1 equals 1. Shift and insert 1 and the state becomes 001. The current state of the cycle 6 is 001 and the output is 1. Feedback 0 XOR 0 equals 0. Shift and insert 0, the next state become 110. So now we observe something important, that we return back to the original state, that is 110. This means the sequence starts repeating. So the generated output sequence becomes 00110, which is exactly same as the given sequence. Now let's calculate the period. The period means after how many bits does the sequence repeat itself. So here it is 6 bits. So T equal to 6. For 3-bit LFSR, the maximum possible period is T max is 2 raised to 3 minus 1, which is 7. But our actual period is only 6. So T is less than T max, which means that this is not a maximum length LFSR. Now let us use this LFSR as the keystream cipher generator. The repeating sequence is 001110. To encrypt a 24-bit plaintext, we need a 24-bit keystream. So we repeat the pattern. 011110, 001110, 001110, 001110. Therefore, the keystream becomes k equal to 111011100011100011100. The plain text is M, and in cipher test the encryption is done using XOR operation. So the equation is C equal to M XOR K. So now let's encrypt the block by block. That plain text is XORed with the key stream. So the cipher text becomes 11111111011101101. This is example shows how the LFSR can generate pseudo-random stream generator for the stream cipher encryption. Instead of directly encrypting using mathematical substitution, the plaintext is done using XORing the generated key stream. However, this is very important weakness here. The period is only 6, which is very small. A small period key stream becomes predictable very quickly. That's why practical cryptography uses multiple LFSR, nonlinear combiners, and more complex feedback mechanisms. So the next question, that you observe the output sequence, that is 001010001010, where the rightmost bit is the first in the sequence. This sequence is generated from a 4-bit LFSR based random generator. Find the seed of the shift register, meaning the initial state, the tap connection C of the shift register. In previous example, we already knew the seed and the feedback equation, but now the situation is reversed. Here we only know the output sequence. From this output alone, we must reconstruct the internal LFSR structure. This process is called LFSR reverse engineering. Here we have a 4-bit LFSR consists of S3, S2, S1 and S0. The output is taken from S0 and the feedback bit is generated using XOR tape. And after every clock cycle, the bit shift through the register. Now let us recover the initial state. The given output sequence is 0010101010. Since the output comes from S0, the earliest output bits directly corresponds to the initial register content. Take the first 4 bit carefully, that is 0010. Now map them to a register. S3 equal to 0, S2 equal to 0, S1 equal to 1 and S0 equal to 0. Therefore, the constructed seed becomes 0010. So now we already know the initial state, that is 0010. But we still don't know which tapes are connected to XOR feedback. Now let us determine the tap positions. We assume that feedback equation as S2 XOR X1. This means the XOR feedback is generated using register S2 and S1. Therefore, the tape vector becomes C equal to 1100, which represents the tapes at position 2 and 1. Remembering the XOR rules, that is same value gives 0 and different values give 1. Now let us verify whether this assumed feedback equation actually responds the observed sequence. We simulate the LFSR cycle by cycle. So in cycle 0, initial state is 0010. The output is taken from S0, so the output becomes 0. Now calculate the feedback. S2 XOR S1, 0 XOR 1 equals 1. After shifting and inserting feedback 1, the state becomes 0101. And the next cycle 1, current state becomes 0101. The output is 1. Feedback calculation 1 XOR 0 equals 1. After shifting, the state becomes 1011. It goes to next cycle and the current state is 1011. Output is 1. Feedback is 0 XOR 1 equals 1. and the state becomes 0, 1, 1, 1. Next third cycle, the current state becomes 0, 1, 1, 1. The output is 1 and the feedback 1 XOR 1 equals 0. So the next state is 1, 1, 1, 0. In cycle 4, the current state is 1, 1, 1, 0. The output is 0 and feedback 1 XOR 1 equals 0. The next state 1, 1, 0, 0. And the next cycle 5, the current state is 1, 1, 0, 0, output is 0, feedback 1 XOR 0 equals 1, and the next state become 1, 0, 0, 1. And the cycle 6, the current state is 1, 0, 0, 1, output become 1, and feedback is 0 XOR 0 equals 0. So the next state is 0, 0, 1, 0. Now observe carefully, at cycle 6, the state becomes 0, 0, 1, 0, which is exactly same as the current state, which means the sequence starts repeating. The generated output sequence is 0, 1, 1, 0, 1, 0, which correctly match the observed output sequence. This demonstrates very important concept in cryptography. If an attacker observes enough output bit, they may reconstruct the seed, feedback equation, and even the entire LFSR structure. That's why standalone LFSR are not cryptographically secure. So finally, the initial seed is 0, 0, 1, 0. Feedback equation is S2 XOR S1 and the connection vector is C1, 1, 0, 0. This simulation successfully produces the observed sequence, hence the reverse engineering process is verified. A linear feedback shift register or LFSR generates the following 50-bit sequence. Construct an LFSR of minimal length that produces this output. Show all the steps carefully. In this problem, we are not given the LFSR directly. Instead, we are only observe a long output sequence. From that sequence, we must construct the smallest possible LFSR capable of generating it. This process is extremely important in cryptanalysis because if an attacker can recover the LFSR from observed output, the cipher can be broken. So, first we carefully observe the sequence. We are given 50 bits, so n equal to 50. Now, the first thing we are trying to identify is whether the sequence contains repetition or periodic behavior. If sequence repeat, then the repeating structures give us the information about the possible LFSR length, the feedback tape, and the linear complexity. A highly repetitive sequence usually means a smaller or weaker LFSR. Now we apply one of the most important algorithm in stream cipher cryptanalysis, the Berlekamp-Massey algorithm. This algorithm finds the shortest LFSR capable of generating observed sequence. In simple words, it tells us the minimum linear complexity of the sequence. At every step, the algorithm checks whether the current connection polynomial correctly predicts the next bit. If prediction fails, a discrepancy occurs and that discrepancy is represented by D. If D equal to 0, then no update is needed. If D equal to 1, then the connection polynomial must be updated. Now, let us analyze the Berlekamp-Massey update table step by step. Initially, the connection polynomial is simply 1 and the linear complexity L equal to 0, meaning no meaningful LFSR has been yet identified. At step 5, a discrepancy occurs, so D equal to 1. This means the current polynomial cannot predict the sequence anymore. Therefore, the algorithm updates the connection polynomial to 1 plus x. Now, the linear complexity changes from 0 to 1. At step 11, another discrepancy occurs, again D equal to 1, so the polynomial is updated to 1 plus x square. Now, the complexity becomes L equal to 2. At step 17, another update occurs, the polynomial becomes 1 plus x square. And now the linear complexity L is 3. At step 21, another discrepancy appears, the polynomial updated to 1 plus x cube plus x4. Now the linear complexity L equal to 4. After processing all 50 bits, no further updates are required. So the final minimal linear complexity is L equal to 4. And the final connection polynomial becomes C of x is 1 plus x plus 1 x plus x cube plus x raised to 4. This polynomial repeats the feedback structure of the LFSR. The non-zero coefficient tells us which stage participates in the XOR feedback. Now let us rewrite the polynomial in standard form. The connection polynomial is x raised to 4 plus x raised to 3 plus x plus 1. This means the feedback type exists at the position 4, 3, 1 and 0. Very important that position corresponds to the non-zero coefficient. So a term exists in polynomial that register participated in the feedback. So the types are at x4, s4, s3, s1 and s0. Now using the obtained polynomial we construct the LFSR. The feedback equation becomes x4 XOR s3 XOR x1 XOR s0. This means the output from those registers are XORed together and the result is fed back into the register. Here s4 is the most significant bit and s0 is the least one. Now we initialize the LFSR using the first 5 bit of observed sequence. The initial state becomes 0 0 1 0 0, which means s4 is 0, s3 is 0, s2 is 1 and s1 is 0 and 0 is 0. Now we generate bits using constructed LFSR and compare them with original 50-bit sequence. The sequence is checked in the block and every generated block perfectly matches the observed bit. This confirms the constructed LFSR successfully reproduced the given sequence exactly. Now this example teaches a very important lesson in cryptography. Even we observe only the output bit, we can still reconstruct the LFSR. This is why plain LFSR are not only secure for the modern cryptography. So in this example, we learned how the Berlekamp algorithm reconstructs the shortest possible LFSR from the observed sequence. So also we learned linear complexity, connection polynomial and type position are determined from the real output bits. This is one of the most important concepts in street cipher cryptanalysis. Thank you for watching ZypherSpaceCore.